1996, and he and I wrote a paper together at that time, the CRTT paper that Chris mentioned in this talk. Although I was not his advisor was David Fetch, who was the co-author of this talk. He's now in Oxford. After graduating, Toby went to University of Colorado for a postdoc, and then since then he's been at the University of Delaware. He's the author of a book looking at Computational on conformal mapping, numerical conformal mapping. He's the author of the best-known toolbox for numerical conformal mapping, if you want to do it in MATLAB. And one of his papers won the SIAM Best Paper Prize for a student in around 96. His areas of research are high-order methods for PDEs and also numerical conformal.
Thank you, Steve. I am speaking to you as a numerical analyst. One consequence of that is I think you'll find all the mathematics to be completely trivial to you. I'll try to be incomprehensible in other ways to make up for it. Nick consented to be my co-author. He wasn't necessarily an active co-author, so if you don't like the talk, you should blame me. But if you don't like the idea for the talk, you should blame Nick, because that's his fault. So the genesis of this talk was a series of email messages from Nick. And the emails were about his idea of 10-digit algorithms. So this comes from a speech that he gave at Dundee NA conference a few years ago, and some accompanying code. And he has an eloquent essay on his website that argues about this. But this is kind of the mantra that goes with it. So you're looking for 10 digits of accuracy. It executes in 5 seconds or less, and you can write the code in 1 page. Now, you can argue about the merits of these things, and I'll let Nick do it himself. I won't try to do so. There is some built-in ambiguity here, and there's also some things that are left out. So to give you an example, the SC toolbox is not a 10-digit algorithm. You can usually get 10 digits. Sometimes you can get 5 seconds. But it's not 1 page. It's not even close. And that's because it's meant to be a versatile tool. It's supposed to do a lot of different potential problems. So versatility is not one of the criteria of the algorithm. And Nick's point is not that all of numerical analysis in scientific computers should look like this, but he argues that some of it should. So in any case, Nick started sending me 10 files that are related to this idea. And I was executing them and giving him some feedback and improving his MATLAB code. And one of the ones that he sent me, I stripped it down somewhat. I didn't apply command out, but this is most of it. It's computing Green's function for the domain that's exterior to those 3 circles. So you have a common value on 3 circles and log z and infinity. And now, if you're fluent in MATLAB, you know where I'm heading because you'll be able to see what's going on. I'll describe my own code later on. But one of the reasons this caught my attention is that at the same time, I've been working with Tom DeLillo and Alan Elfrat and John Faltzfrat on the Schwarz-Stoppable formula for multiply connected regions like this. So to map from something very exactly like that to the exterior of some polygons. And Tom and John and Alan did all the theory behind that. I've helped them with the merits. And it's been difficult. The formula is more complicated to write down. We've got infinite reflections going on mutually in all the components. It's more difficult to program. We have a parameter problem. Sometimes we converge to the solution of that parameter problem. Sometimes it's even the right solution. Not always yet. I have no doubt that these things will get better, but at the same time, it's just a lot of work. It's just complicated. And then Nick throws this thing up in this picture. So it got me wondering, maybe I should be paying attention to this and see if there's anything in it for me for these types of problems or other types of problems. So let's start with an easy problem. Let's say we want to map this blob to a half plane. And I should say that all the figures you're going to see in the whole talk are quantitative. So when I talk about mapping this region, that's literally the region that I'm mapping. Now, at some point on the boundary of the blob is supposed to go to infinity, because that's on the boundary of the half plane. So I need a simple pole to do that. The tangent, you see that dashed line up there, the tangent at that point tells me what number I should put here in order to get the thing to be horizontal and infinity. That won't make the entire boundary horizontal, but it'll be horizontal as you go to infinity. So the remainder has to be picked up by some analytic part. Okay, but because that remainder is analytic, I can approximate it by a polynomial. And polynomials are spectrally accurate approximations to analytic functions, so I should get exponential convergence as the number of functions in my basis increases. Okay, so what does this look like? So this is the most math we're going to do today, like I already said. So let's, now instead of picking a variable z, let's discretize z around the boundary. It's not particularly important how, I think. And then we'll evaluate those same basis functions. So I'm thinking of a combination of this guy plus these. Each one of those gets its own column in a matrix. Okay, so this matrix is the number of discretized points by number of basis functions. And then my f is approximately the expansion that I'm using is a times the vector, where the first component of that vector is known to be a 1. Okay, so I want to impose some condition to find those coefficients, and the condition is that the imaginary part of f of z on the boundary is constant. So in order to extract the imaginary part of the map, I break A into its real and imaginary parts. I break the coefficient vector into its real and imaginary parts. And now I have a statement about real matrices. Okay, and then if the imaginary part is constant, that means pairwise differences should be 0. So I'll take this Toplitz matrix and pre-multiply the whole thing. And that should give me 0 in the vector sense. So when I lump these two matrices together, I get some other matrix B. So it looks like I have a problem where, so B is the same size, well actually it has twice as many columns because of the real imaginary decomposition. So it's number of points, 2 times the number of basis functions for columns. And that times C is supposed to be approximately 0. So that sounds like an easy problem to solve. Except that, of course, the first component is supposed to be 1. So I take the first column with B out and go to the other side. And then I have a standard least squares problem. So here's my comparing with my code. I'm loading in a description of the boundary, which is just a parameterization that kind of trigonometric interpolation of just points. I'm picking the first point to be the pre-image of infinity. Here I'm loading up the matrix of A with its columns, basis functions. I don't even need to formulate that Toplitz matrix here. All this does is take differences of adjacent rows in that matrix, and in MATLAB you can do that with a diff. Then I impose the boundary conditions, so the real part of C of 1 is 1, the imaginary part of C of 1 is 0. So I delete the 2 columns for B. Backslash solves in the least square sense as well as it solves for square matrices. Reinterpret things in complex numbers, and then I'll look at what happens when I map the points on the boundary and take the norm of their imaginary part as a measure of my pyramid. And so there we do see spectral convergence in those things you get. So the scale over here is 10 to the minus 12. Those are far less than 5 seconds. So here's a tangent algorithm for the blob map. And you can set the bar very high with that region. Let me try something somewhat more complicated. Something that has an elongation of the order of 12 or 15 constant ratios. Now what happens is when I do the same function, I get a short period of spectral convergence again, and then it just kind of mellows out and doesn't get much further. And when you run the code, you see at this elbow, where the convergence stops, you see warnings from MATLAB about condition numbers. So the condition number is telling you that the columns of the matrix are really dependent, which in retrospect is no big surprise when you use monomials on that region. In fact, I need one detail on that. I'm actually rescaling these columns to have norm 1. If I don't do that, it's even worse. But even with that rescaling, it's not enough to save this as a basis for approximating the solution. Well, this thing is vaguely interval-like, or ellipse-like, so maybe I should try Chebyshev problem. Okay, with a scaling factor in here, they've got things like -1 to 1. When you do that, because it's just as easy. Now you see, of course, they agree at the beginning because they're spanning the same space. But the only difference is that this is a well-conditioned basis for that space. And another basis is a poorly conditioned basis for that space. So Chebyshev marches on downward. But I'm not getting 10 digits. I'm getting 10 to the minus 8.
Excuse me.
Yes.
The strip at the top is the domain?
Yes. I'm still not going to do that. And the reason, I guess, is that the Chebyshev polynomials are pretty good, but that's not really an interval. Not really an ellipse. I suppose what I ought to use are Fowler polynomials, but I don't know how to get those without the conformal map that I'm trying to find. So what do I do? Is there any way to rescue this basis and push all the way 10 digits or more? And so the answer comes from perhaps a surprising direction.
So, Toby, just to understand, that was the problem with round-off theorem, right? Basically. In other words, if this were infinite precision, then you would get your
So we're infinite precision. Right.
Okay, cool.
It's just a question of basis. So one answer to this problem is the Arnold iteration, which is very familiar to numerical analysts. I don't know how familiar it is outside that community. But the Arnold iteration comes from solving large linear algebra problems. Linear systems are eigenvalues, where A is a very large, sparse matrix. And instead of trying to do Gaussian elimination, which is too slow and doesn't give you anything until you get to the very end, you instead look for approximate solutions in what's known as a Krylov subspace, which is the space spanned by these vectors. It turns out that this space has pretty good approximation properties for these kinds of problems. So the question is, how do you work with this space? Because these vectors become more and more parallel to the dominant eigenvalue. It becomes ill-conditioned. And so the Arnold algorithm is really the QR iteration. I'm sorry, it's the Reentrant Orthogonal iteration. But the clever part is in this line, the first line inside the loop. The clever part is in how you get the original basis function. Because if you wrote down the matrix K, let's say, that had these as columns, as soon as you discretize that, you're dead. You've lost the information numerically between, let's say, a to the 50th times being an a to the 51st times. But what Arnold says is first, orthogonalize this, assume you've got this orthogonalized, and then take the last one and multiply by a again. And what you have is not purely a to the n b, but it's got something in that direction. And that's all you need. And then you orthogonalize with that. So, like I said, this is well known to numerical analysts. And the interesting thing is that you can apply it for polynomials, orthogonalize them. The operator A becomes sort of pointwise multiplication. You think that as a diagonal matrix. So this x dot star is really the same as diag x times q. Everything else there is just standard Reentrant. If you do this where x starts out in the interval -1 to 1, you get Legendre polynomials. And you could do weighted least squares, the Chebyshev polynomials, and so forth. So I want to do this in the case where x is not just -1 to 1, but it's the boundary of these regions. When I do that, the polynomials bow out quickly. Chebyshev bows out after a while. Then Arnold just keeps on trying.
So let's add that thing. How does the boundary domain come into it? It's incorporated as A matrix somehow?
It's entirely through the discretization of the first line. And that tells you what the region is.
So how? That's, I'm sorry.
So
That's
those are
complex numbers and...
Right. Those are in this case it's just points from -1 to 1. But in general, it's it would be this line here that takes the CB, which is my parameterization of the boundary, and evaluates it.
So it's evaluation along the boundary.
Yeah.
And in this iteration, is that going into the B or going into the A?
It goes into the A, and then B is constructed. So in fact, what you would do is you replace this with the equivalent of that Arnold code.
I'm sorry, I don't know MATLAB at all. We don't.
Okay.
I don't know MATLAB licensing on the front.
Is it obvious that polynomials are the right basis in the first place, or a strip like that?
No, they're a natural basis, but I don't know that it's a right basis. What is the right basis?
I don't know. I mean,
Good question.
yeah.
I mean, if I had it, I would use it. I only have, this is a numerically derived thing. The downside is that I can't write down what the coefficients of these things are in terms of the monomials, something like that. They're derived numerically. But they are perfectly adapted to the region. To boundary conditions. Okay, and I just want to make a side comment that this idea of a basis which is spectrally accurate and yet exponentially ill-conditioned comes up a lot in numerical analysis. In fact, at least one of these areas, you see the term uncertainty principle. Well, you can't be accurate and well-conditioned at the same time, it seems like, in many cases. And in those cases that you can, those are the famous examples of spectral methods. So, I mean, the classical example is the monomial basis on -1 to 1. It doesn't work, but when you use Chebyshev polynomials or Legendre polynomials, it works beautifully. Another area that I'm interested in researching is radial basis functions. So a radial basis function approximation, the basis members are functions of distance from a central point. So in one dimension, you can imagine you just have the bowls centered at your interpolation points. It turns out that these things are spectrally accurate in the limit where the bowls are extremely shallow. But of course, if the bowls are shallow relative to the spacing between them, they're hard to tell apart, and so you get an unconditioned basis. And there's a lot of literature on that. Historically, these are used for surface interpolation, but people are, including myself, are very interested in using PDEs. So these are just a few representative names of people who have worked on this problem. Another example would be the charge simulation method Mono uses for conformal mapping and line-dependent problems. So there you use fundamental solutions like logs for the Laplace's equation. You place the sources outside the domain of interest, and then all you have to do is collocate the boundary conditions to get an approximation.
So just for numerical analysis of dummy, I want to make sure I understand that.
Okay.
You have some solution you're trying to approximate and some collection of things you're using to approximate. You're saying it's spectrally accurate. In theory, you can get a good approximation from that collection. And it's numerically good if those collections are sort of sufficiently different from each other that you can do linear algebra with them. It's spectral.
That's pretty exciting. I think you understand it pretty well. With the charge simulation, what happens is that you get the most accuracy when the charges move far away from the domain. But of course, then their effect on the domain is hard to distinguish, so you get ill conditions. Kitagawa has a very well-known analysis of that, I believe in the 70s or the 80s. There's also a very closely related method of particular solutions for eigenvalue problems. Timo Becky is another student of Nick's who works on that problem. Alex Barnett at Dartmouth does amazing things with it. But they're running into the same issue. You can get something which is very accurate and yet hard to compute with conditioning. Something similar happens if you use Maxwell's equations, if you use combinations of plane waves in different directions to represent the solution. Again, it's accurate, but with the accurate limit, you also get no condition. Now, I want to go a step closer to harder problems, and one of the things that makes the problem harder is a corner. This came up in Chris's talk yesterday. If I have a corner of pi alpha and I exponentiate by 1 over alpha, I smooth the corner out, and by Schwartz reflection, the function is now smooth in this variable. So I can expand that further. Of course, if alpha was 1 over integer to begin with, right, you could have reflected all the way around and matched up perfectly, and so the whole thing is analytic in the original. So let's map to a triangle. So this is not a special triangle. I literally just put 3 points down with the mouse. The angles are effectively irrational. So out of one corner, I want to exponentiate 1 over alpha 1, and then take powers of that, expanding that variable. And of course, I'm going to orthogonalize as I go. And then I do the same around each of the other corners, because the exponentiation smooths out this corner. It doesn't affect the other two because it's conformal everywhere else. And so each of these has to be exponentiated out.
Okay, so then just to slow down for me.
Okay.
So you're taking the sequence of powers and losing Graham Schmidt at each stage.
Right.
Well, I guess what weight? Against area measure or length measure on the boundary, or what's?
Implicitly, I guess it's length measure on the boundary because I'm linearly spacing them. You could tinker with that to your heart's delight.
Just one. Yeah.
Yeah. I mean, you might want to play with that, but I'm just trying to walk first. And one big problem I identify here is that I can orthogonalize each of these independently. I don't know how to do this process or orthogonalize them mutually. In other words, I don't know how to get the span of powers of these guys, and these guys in an orthogonal way. So I literally have three matrices that have condition number 1, then I have to paste them together, and they no longer have condition number 1. And my worry, and this is played out in some examples, not this one, is that as this n gets very large, you once again find that the information in these 3 is reductive. That's not as deadly as it has to be because least squares is very forgiving, right? If you have a no-condition square problem, you probably can't get a solution. If you have a no-condition least squares problem, what happens is that, well, you just disregard the columns that go to your end and So that's why you get these curves that converge to a point and no further, but they don't go up either. So as long as one of these is giving me some new information, even if the other 2 aren't giving me anything beyond that, I might still be all right. I'm wasting effort, but I think I might still be able to do it. Certainly on this example, it's no problem. Although I can get 12 or 13 digits, but no more. I don't know why this seems to be happening. Okay, so once you put corners in the source domain, it's natural to think about putting corners in the image domain. So let's take our blob again with the 4 distinguished points and map those to the corners of a rectangle. Classical problem. Well, each of these points is going to map to a 90-degree angle, so I have to square root. And I'm only going to take odd powers that I have because the even powers are analytic, and if I combined all of those, I'd be wasting information. So I'll do odd powers at the corners plus an analytic part to pick up on that. All right, so that's all the singularity structure I should need. On the image side, what do I have to do? Well, for some points, I again have the imaginary part is constant. For other points, I want to impose that the real part is constant. So for points on one side, let's say on the long side of the blob, I want that to correspond to points here, so I'll take differences of the imaginary part, set those equal 0. So on all the way around. And again, I get spectral convergence to about 12 digits. Here you can see, I don't know if you can make them out, these black dots are what happens to equally spaced points around the blob from the north.
Are you adjusting the aspect ratio of the rectangle?
No, in fact, that comes out in the solution. That's why everybody asked this question, but in the half plane, I could have just imposed that the imaginary part was 0. Right? But anticipating this problem, all I wanted was to say that it was constant, so the differences were 0. So I don't know in advance. I mean, I can specify 2 of them, right? But otherwise,
points on the blob are fixed.
yes. You assume the points on the blob are given. So all I know is that they're constant. I don't know what those constant are.
But you use some constraint like one corner is tied down, so your intervector is drifting around the plane.
Well, you can do that, or you can just take out the affine part of the second one's better.
How do you measure the accuracy?
Good question. At this point, what I'm doing is I'm solving.
You're seeing how close the images are to these constants. But he doesn't have a true control back comparison. That's how straight a line you are.
I'm trying to solve this problem in least square sense, and what I'm measuring now is just the residual. And that actually measures basically how well this differences around the boundary approximate 0.
Are you still under the 5 seconds?
Yep. Here we go. Even on this laptop, I think we're doing it 5 seconds, and this is 2 years old.
This is junk.
fancier way of putting singularities in the image region. Same blob, same points. Now, right, so that previous case, you can think of this, if you take the real part, then you have Dirichlet values on these two and Neumann conditions on those two. Because when you take the real part, the y derivative is 0. It is horizontal edges. So let's say instead of 2 Neumann and 2 Dirichlet, we go Dirichlet, 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 Neumann. Well, each Dirichlet side, I'm going to take the real part of f as my solution. So each Dirichlet side should be vertical. Each Neumann side should be horizontal. And I know, furthermore, that in the first case, the real part should be 0. In the second case, the real part should be 1. And in the third case, the real part should be 3. So, when I make a transition from 0 to 1, that's instantaneous, so that's a singularity. And it turns out that that singularity is logarithmic. So, just looking at that upper left one, if I take the log of z minus that vertex, which is flat at that, the boundary is flat at that vertex, then I get a jump in argument of pi. So if I divide by pi, I get a jump of exactly 1 from there to there. Right? So I'm going along 0, I'm traveling down this edge. When I hit the vertex, I get it to infinity. And then as I travel along 1, I come back up this edge. At some point along this long edge, I turn around at the top of that slit, come back down to infinity. Right? Then I make a transition over to 3. I come up, I hit that last corner, I turn left, so that I get a horizontal edge, which is Neumann, and then I completed my transit around the module. So for each of these transitions between Dirichlet conditions, I have a known jump, and I put that in with the logs. These other two corners, I know I have to have 90 degrees, so I take square roots. Powers of those square roots. I don't need powers of the logs. The log is the entire singularity. I need powers of the square roots. On the image side, again, I just have that the real part is constant in some cases, and the imaginary part is constant in other cases. Now, this kind of solution of boundary value problems through this type of conformal map is in my book on Schwarz-Stoppable map, because normally we think of the problem being in the disk, and the solution is a Schwarz-Stoppable. And it's a Schwarz-Stoppable map, like the rectangle, is what I like to call a discovered geometry. You know some things about the problem, where the real parts are, but you don't know everything about the geometry. For instance, you don't know where the top of that slit is supposed to be. And that's just discovered as part of the solution process. Nevertheless, you can do it as a Schwarz-Stoppable map, and it's actually easier than the usual parameter problem. But I'm just going to skip the middleman here. I'm just going to go straight from the original domain to the solution, this expansion. And now I'm not quite able to eke out 10 digits. I don't know what this is either. But I'm getting 9, awfully close to 10. Of course, you have to ask what more are we talking about, really? I don't know. I'm getting, but if you look at the number of orders of magnitude, it's about 9. It's not quite 10. And I suspect that's just because I'm losing orthogonalization with these two, but it could be I'm doing something else fundamentally wrong.
Just to make sure I understand this picture.
Okay.
I was completely confused until the last few seconds. You're mapping onto a half-infinite strip, so this rectangular picture actually goes all the way down.
Right.
Thousands, millions of miles now. Not just the
Google's
first
response.
one.
Yes.
Okay.
Yeah.
I didn't realize that.
Yeah, maybe this colors are a little too subtle. There's yellow on these three sides, but there's no yellow down here.
So there's only 2 red dots in this picture. The other 2 are at minus infinity.
Exactly.
All the way down.
And one of the interesting things, these are so much fun to play with, because when you've nailed the problem, you know it. Right? You just get those beautiful curves. I don't think I've quite nailed this one.
How many points are there on the boundary?
What's that?
How many points are you taking on the boundary?
I think it's 800 here. Mostly what you want to do is to keep a good aspect ratio in the radius. You want at least 2 to 1. It's a rule of thumb. Now here's something that I couldn't do before. It's a little bit complicated. This is a paper by, I don't even know how to pronounce his name, Preference? Does anyone know his name? The paper I picked up from the conference.
Not enough vowels.
Yeah, exactly. It's I think in the 20s or 30s, and it's about solving Poisson's equation, or if you subtract off a particular solution, finding a harmonic function where the boundary data is not constant, not even piecewise constant. It's piecewise polynomial. Well, Trepetz's idea was that if you define V to be the real part of some F, then it turns out, in Cauchy-Riemann equations, when you look at the real part of F double prime, you're just taking tangential derivatives of V. And that means that the real part of F double prime is actually piecewise constant. Now, in this problem, I posed it on a square. It's not important that it be a square. It does have to be a polygon. Otherwise, these don't come out to be constants. Okay, so V is the real part of an F. The real part of F double prime is piecewise constant. That means F double prime is one of these maps. In this case, I actually do know the whole geometry. And at this point, Trepetz knew all this. He knew that F double prime was a Schwarzschild map. He found for the Schwarzschild map. And then, it's just the 1930s. That's the end of the story. And even for me, it was the end of the story. I mean, sure, I could find that map very quickly, but I don't want to integrate it twice. That's not a good method. But the beauty part is now I can integrate before I solve. So if I know F double prime has to solve this kind of problem, I know it has these log singularities. So I integrate it up twice, and I get z squared times log z times singularities. Everything else is analytic. Again, I know the jumps. It's a little bit more complicated because I start at 90 degrees, and I want to jump by 2, so there's a factor of 4. When I integrate, that 4 becomes easy. But in any case, the important thing is I know the strengths of all the log singularities. Everything else is analytic when you solve for it. There's fourfold symmetry, so I guess that's why I get 4 at a time. But polynomial degree 24, so you can solve these Poisson problems if you have a particular solution. Now let's go back to maps. So half planes are great. Disks are often more convenient. Of course, I could map to the half plane first and then to the disk, but let's discard that mentality. We're going to go straight to the answer. If I try to map straight from the blob to the disk, the condition would be that the modulus of f of z is constant. That's not a linear condition. Right? So you could solve it, but now you're doing an iterative method. It's non-linearly squared, it's much harder, much slower. However, if you take a log, the boundary of the circle becomes vertical. I get these branch cuts that are identified. It's no problem. It's just telling me that the log f has a log, whatever point I want to map to the center of the disk. Everything else is in there.
So you're not looking for the Lillies transformation that happens to this, but you're looking for the logarithm.
But I'm taking a logarithm to go straight to the answer. So in other words, rather than finding an answer and then modifying the answer, I'm just going straight to the answer. And I'm going to stop showing convergence because it always looks the same. But just to maybe convince you that I've actually done this. Exterior maps, same kind of development. In fact, everything looks almost exactly the same with a log at infinity, assuming infinity maps to infinity. Everything else is analytic at infinity. So that's your basis. That works too, but I'm not showing you the convergence. So now I'm finally ready to get back to that Green's example that was bugging me at the beginning. Nick did 3 disks, so I'll do 4. So I have these 4 circles. How am I going to represent the map from these circles to the exterior parallel slits? Okay. Well, I'm going to assume that the derivative of the map is 1 at infinity. And everything else I'm going to represent, it's analytic in the exterior domain. I don't need to do it this way, but it turns out to be nice to do it where I take powers, inverse powers, after translation by the centers. In other words, it's like a Fourier approximation on the disks. Just turns out to converge. Of course, on the image part, I'm just going to impose that the real part of the map is constant on each piece. So again, differences in the real part are 0. And they don't have to be vertical slits. They could be at any angle. I could do those just as well. So one question I haven't had so far is what about the interior? I just solved it without the boundary. So this is to convince you I can solve for it in the interior as well. So I'm mapping these 4 disks to 4 parallel slits, which of course corresponds to the solution of a flow problem. So I can take streamlines. This is a contour map on the left. Those are streamlines in the flow. Past those bodies. And just to convince you that I can also do these when those are circles, I can still do corners. Right? I couldn't do maybe 20 corners each, but I can certainly do 3 or 4 corners each mapped to this parallel solution. And in terms of how well this works, I mean, in our Stoppable experiments, we had 2 slits that were crowded this closely together. I think we would start working. But I can actually get them much closer than this using this least squares.
Can you comment on what you just said about the interior? Do you actually do that during the computation, or is it after you've computed on the boundary, you reconstruct the interior?
So you can do it, depends on how much accuracy you want. I mean, in this case, cheating a little bit, I didn't do the Arnold at all, just without the orthogonalization. If you have orthogonal lines, right, that's telling you multiply the previous one by z and then recombine them according to these coefficients. You can do the same thing with points that you picked in the interior as well. Right? They don't factor into the orthogonalization, they just go along. You just do the same combinations for those. But you have to pick the points in advance. That would be the one restriction. So it's more like a classical collocation method where you have to say in advance where you want to know the solution. Now, one of the challenges that I haven't attempted to address yet, this is the last part, is what happens when you have reentrant corners. So, you know, I went mildly crowded. I didn't go terribly crowded, and I think that would be hard if I did. This is hard too, and maybe the reasons are the same. I don't know. And I think probably a lot of people here have better intuition about this than me. But let's say I map the disk from an inverted ellipse, which we know that map exactly, and we know that that has square root singularities along these 2 branches. Now, it looks like those branches touch the boundary, they don't quite, but they get within about 1% or something. So the fact that they're so close to the boundary, technically the map is analytic in the inverted ellipse, but of course, the singularity is so close to the boundary, this looks like convergence until you read the scales. 10 to the minus 0.1, 10 to the minus 0.2, 10 to the minus 0.3. That's not convergence. Well, in this case, maybe what I should do is to say, even though those singularities aren't part of the boundary, you know, they're so close that they might as well be, and I should put those functions in anyway, smooth them out. And when you do that, I wouldn't say this is outstanding convergence, but it's good convergence. Clearly, it's 10-digit convergence. Yes, it's still under 5 seconds, with about 200 basis points. Now, this is maybe the most favorable case because I know everything about the map and know exactly where the singularities are. Now I'm definitely running into terra incognita. Let's say I have this U shape. It's slightly elongated, but that's not the real problem. I think the real problem is the cavity there. So, you know, if I just go ahead and map the U, well, I get nothing. No progress. So I suspect that there's some singularity structure in there again. I don't know what it is. But I just click with the mouse and assume I had a branch event starting at that point. Okay? And you can see I get some convergence, but I'm only getting about 2 orders of magnitude. It's not the right thing to do today. So it's kind of the right idea, but not, so it's maybe right in generality, but certainly not right in the specifics. I don't know, at this point I don't have an opinion as to whether this can really be fixed. I mean, you can think of this as sort of a preconditioning step. Right? I take that branch and I smooth it out, or you think of it as a disk. Right? Those are Stoppable maps, so if I had multiple branches, I could still do that. But you see that the points are still very, very close to the boundary of the disk, so I'm still not getting very good convergence. And maybe some of you have a good intuition as to what I should, you know, maybe I should map those points again, move them away from the boundary a little bit farther before I do it. Maybe I should just do a couple of iterations of zipper. I don't know. Precondition it. Then I have to think about how am I going to locate these singularities. So another of Nick's students, Win T, was doing adaptive simulations of Berger's equation on the interval, and he found that he could locate singularities that were coming close to the interval by pad A approximation. reproduce it very nicely. So maybe that would work here too. Pick a few points, compute the rational interpolament for those points, and look at the poles of that as guesses for the singularities of the exact function. Maybe this has to be done through some kind of feedback. You try to do the math, you get a little bit more information about the singularities, and then you can use that for feedback. At this point, I don't know. And maybe this isn't appropriate for Cambridge development. I'm not sure I can try. Let me just finish by acknowledging some of the people. None of this, I would say, none of the mathematics, certainly, or even the algorithms, is original to me. I'm just trying to put this together in names. These are people who helped shape my thinking. So thank you very much.
Questions?
Yes, I have kind of a big picture question. So you're showing whether you got convergence or not, but I'm wondering, is this also about approximation and interpolation? So if someone told you, oh, use this many triangles and I'll tell you exactly, with infinite precision, the coefficients for the basis functions, would you still have similar pictures of how well you could approximate the solution?
Well, at some point I'm going to notice that it's discretized. I'm not quite sure what you're asking. But, I am depending on the boundary really being analytic or analytic plus a few corners. Maybe that's not what you're getting at.
Well, take that last picture where you couldn't get as much convergence as you wanted.
Right.
Do you think that's so what if you reran that into precision?
Oh, if I ran it at infinite precision, I would expect that this continues down. Sure. The map is analytic on that region.
But do you have enough terms in your basis?
Well, I think this is the true convergence rate. I can't prove that. But, I think if I had infinite precision, I do get warnings here. I think if I had infinite precision, I believe,
so the leveling off is due to numerical error,
you know what?
but then the slope of the first part is due to approximation.
No, I think I have that completely wrong.
Oh.
I think it's actually that I have the wrong basis. So I think that for a while it looks like this, but I think this is actually the asymptotic convergence rate. It's not. So I'm completely disregarding everything I said before. I think this is actually what you would get in infinite precision, and if you were infinitely patient, I guess it converges.
This has the Arnoldi or not?
This does have a running. Yes. And it's not much of an issue because there's only one corner, so it's definitely an orthogonal.
We're just looking at this one U picture. It reminds me very much of the medial axis type of pictures we were seeing yesterday. And one thing you might try, maybe it's too big to be applicable, but do something like the medial axis for the outside. And edges of the medial axis and the corners then tell you, oh, here's a corner, you got to open that up in the singularity. But also the edge of the medial axis that goes on a channel like that, so you need some kind of branch to open that up. And maybe one singularity per edge of the medial axis to the exterior would be enough to sort of roughly flatten.
That's an interesting idea because when I look at peek at the pad A singularities and they don't lie on a nice smooth branch cut, maybe something like that is the right curve.
Somehow, not straight line branch cuts, but branch cuts that follow the medial axis from inside out to
right. Again, that would be kind of a Schwarz-Christoph idea.
Maybe you take the medial axis, make a tree out of it, and apply Schwarz-Christoph as a complementary domain of the medial axis, and that's your first approximation around off.
Right. Medial axis of the outside.
Of the outside. So take the medial axis to the outside and sort of complement the simply connected domain, apply Schwarz-Christoph to that, and then somehow that makes the complement around the disk, and then you should have maybe taken care of everything. So maybe your map is sort of analytic plus Schwarz-Christoph will apply to it.
In this case, I don't think there was an analytic plus because this thing's already analytic.
Yeah, well, lots of handling.
Okay, that's fine.
Like, I like your talk very much, but sometimes it depresses me when I think, well, I thought about control mapping, but there's a whole universe of other things to think about, which now occurs to me. Numerical stability.
Yeah, I can't see. Maybe you have some dots on the pictures that we can't see. So, but you've chosen, like in that U, you've chosen the points on the boundary ahead of time, right? And really, those should depend probably on the preconditioning you do. Is that right?
Good point too. Yeah. Certainly, I haven't attempted to play with that distribution at all. that might
There
be.
should be some interplay between the points you choose and the preconditioning or the pre-maps you're
And
going
why
to
use
apply.
the map? It's you approximately the correct positioning up to a folder error. And we'll pile more and more things on and turn your one-page of code into 100 pages of code. Which ones, in 5 hours and not 5 minutes. But it'll get you at least 1% closer to the answer.
So Ken, I heard Ken this morning talking about what a difference it is to go from 3 days of computing to 3 minutes of computing. And I think there's another difference from 3 minutes to 5 seconds because, when it's 5 seconds, you don't have time to respond to email or anything, right? You ask for the solution, you get it, you make adjustments, right on the fly. Different kind of computing. It's addictive.
Well, I find just when I'm using my computer from home, on the next one I can type and it appears as opposed to when the letters appear about 5 or 10 seconds after I did it. It changes my enthusiasm level quite a bit. Typing a man. Any other questions?